Hash tables are effective for caching, database joins, even partitioning distributed databases, sharding, sets to check if something is there or not. It's very, very effective, even load balancing. A lot of programming languages implement that in-house, in natively in the language. You can build these hash tables. However, what I want to discuss in this episode of the Backend Engineering Show is the limitations and the cost of using hash tables and things that we really don't think about. It comes back to the leaky abstractions of, hey, there's a black box, it's fast, let me use it. But we don't understand how it works. And when you don't understand how something works, you can get away with it. But sometimes when it doesn't work, that's where you really get screwed. And that's where really a good engineer is identify him or herself from the other engineers. How about we jump into and discuss this? Welcome to the Backend Engineering Show with your host Hussein Nasser, and this is our laid-back, chill discussion podcast kind of video audio format. If you can listen in the podcast, if you're listening on Spotify and Apple Podcasts and Google Podcasts, you can listen on that. And this is just basically I don't include graphics or I don't include anything. It's just a long form discussion about one topic, and I try to go as deep as possible to my extent of knowledge on this topic to tease apart this topic. Today's topic is hash tables. In order to discuss what hash tables are, we really need to understand what arrays are. You might say, Hussein, I don't care. I understand what arrays are. Do you think I'm dumb? I know what are arrays and I know how they work. You'll be surprised that we take a lot of things for granted. Arrays is one of them. The concept of array is a consecutive slots of memory. And this is the key word, memory. You cannot put an array on disk. It doesn't make any sense, right? Well, until Ultra RAM is a thing and we can do byte addressability in the disk. But arrays are a property of the random access memory, And the power of this is because it is consecutive. No matter how large the array is, given the index, I can go to the first node, to the first element of the array, or I can go to the middle one, or I can go to the last one, or any element in almost constant cost, big O of 1, as the computer science guys say. It's so fast because of this byte addressability, because every index is associated with a memory address, and to get the next one is literally just add 1 to the memory address and we can get there. And if you ask the CPU to fetch a value of that, whatever the element has, whether an integer or a string or anything, you can immediately go there and fetch the value. And that's the power of the array. And hash tables are nothing but a glorified arrays, to be honest. So you can ask the CPU to fetch a value from an array in memory by giving it its index. From the index, we're going to find the first address and going to add X amount of value, to find that particular index. So the cost is an addition plus the cost to go to the memory from the CPU, right? So the first one is constant. Addition is cheap. It is done in the CPU itself. The other cost to actually jump to the memory is really depending on your architecture of the CPU. And we can really dive deep into this. This is probably another episode itself. The cost to fetch a value from the RAM to the CPU really depends on the distance from where the CPU lives, the memory. In multi-core architecture, you have multiple CPUs and you have a single memory, and they compete in the memory. Only one CPU can access the memory at a given time. And so there's some sort of a competing going on. So what happens is in some certain architecture, there will be two memory locations, right? And in each CPU access its local memory, and that's obviously becomes faster, right? Because there is no competing anymore. No CPU is competing on the memory. The problem with this is now this CPU sometimes might need to access a memory all over there that is available, that's closer to other CPU, and that's what is called the NUMA architecture, the non-uniform memory access. So this can be slow, and this is where guys like Apple is innovating to making the cost of accessing the memory as fast as possible by having everything into a single SoC chip, which is the M1 Pro. And then they just came up with an M1 Ultra, which fuses two M1, SoC chips, such that the cost to jump between different memory is negligible. They just made this great, design such that you don't, as a programmer, you don't really need to, if my array is all over there, I really have to execute my code on this CPU. This is the NOMA aware programming. Obviously, this is a little bit of discussion. We can go into other day, but the cost is, you can't call it constant. It's fast. It can be faster in certain architecture. So that's the array. The problem with the arrays is it's an integer based, right? So 0, 1, 2, 3, 4, 5. So if you can have your key as that index, you won, right? The problem is, like, how many applications where the key is actually an integer and it is actually this particular index? It's almost very little, right? This is where hashing table comes to use the concept of arrays in a very intelligent manner. What do they do? Second example. So I have, I have an ID student, and I want to find their name. Let's say this is a key value store, The ID is obviously a large number, has nothing to do with the index. So what you do is giving the ID, I want immediately to find the name of the student. So the value is the name, the integer, the key is the ID of the student. So given that ID student, what you do is you build a hash table. What do? You effectively take the IDs and you create a hash off of them using a hash function. And that gives you a garbage value, right? So that if you hash the same value again, you're going to get the same hash. Given that hash, you then take that value and then calculate an index that points to an array. That's the trick. And the most easy way is to do a modular function. So let's say your hash table size, your array size is 10, So if you calculate, if you give it this ID, you do modulo 10, you do a hash, and then you do modulo 10, and you get a value between 0 and 9. And that's the power. Because you eventually have an index, you can immediately go to that array value in that index and pitch the value, which is the name of the student in this particular case. And that's the power of hash tables. And so now, given an actual key, I can find the value using the power of array. Well, you might say, there are problems with this, obviously, right? It's like about collision, Sometimes I might get two student IDs that maps to the same hash, which then maps to the same index. Well, that's your responsibility to solve, and we're going to talk about this in the limitations option or portion of this video. So now we know hash tables. So then now we understand hash tables, the idea of hashing something to eventually get an index, which we're going to use to point to an array, which has our values. So one popular use case is database joining. So if you have two relations and you want to join these relations based on a foreign key, you're going to use the idea of hashing, hash tables. Let's say you want to join the company table to the employee table where you have a company ID field. So this employee belongs to this company, right? So in order to join these two tables, you're going to pick one of the relations and you're going to create a hash table. And focus on this word, create a hash table. The hash table doesn't exist. You create it, and there's a cost to creating a hash table. So usually in a join, you pick the smaller relation because creating hash table is expensive because you gotta loop through every single one and take the value, hash it, and get the index, and then go to that array that you hopefully you have already pre-allocated, and then store the value for that index in that particular array. And you're going to do everything for every single value. So that means the hash table really has to have a fixed value to start with. You start with, I'm going to create, I think this relation is around 1,000. Right, it's going to increase 1,000. If you know the size, that's even better. And you say, okay, I want a thousand array element. And so you ask the RAM, hey, give me 1,000 integer consecutive array values. And then you start building the hash tables and you fill all this 1,000. So the first value might go to index 999. The second value might go to the index 78. The third value might go to index 0. And you start filling this hash table. So now, once you've built that hash table, you have a beautiful array in memory with indexes, right? But your hash values mean something. There's a mapping between the hash, between the key to the hash, obviously, and then between the hash to the index. And that mapping is what's critical. Now, okay, we have this hash table. What do I do with it? Now you go to the other relation, whatever it is the company either or the employee, whatever is larger in this case, and you loop through it. You pick the first entry of the company ID. So at this point, you don't really know the value. You're just picking one value by a time. Oh, this is company number 705. Let's hash it and let's get the index by using a modulo, right? And then, it's index number 773. Oh, let's go to the memory, right? Let's go to the array. So ask the CPU to fetch that value. And then when you fetch the value, you get that company complete row, which is the name of the company, the whatever, how many employees, whatever. You've put the entire row that you need. Obviously, you don't put the entire row. You put exactly based on the select query that joined, so that there's like a blob field. You don't just put it if the user didn't ask for it, right? So that's why select star sometimes kills the performance, because look at all this stuff that it needs to do, right? Has to put in the hash table, has to fetch it from the database, from disk. So select star is really harmful. Starting not to do it if you don't need to. And and you start just probing. This is the second step. It's called probing. You probe. And this probe is cost big of one, because it's very fast. Because the hash has a cost, it's constant, and the go and give me that index also has a fixed cost. Again, depends on whether you're NUMA versus not NUMA architecture and your CPU and how far your CPU is from the RAM, all that jazz. But it's almost, let's say it's constant, right? If you're at that stage, that's where you basically optimize. That's a different level altogether. Frankly, above my head, it's just so much details. But yeah, you go there and you fetch the value. So now, if you found the value, that means there's a match. If you didn't, that means, hey, this value doesn't exist, so I don't join it. And you create an output relation as a result. That's how you join. That's a hash join. Obviously, there's optimization in different hash joins, and I think I'm going to make another episode talking about hash joins, because they're like methods. What I just explained is the classical hash join, it becomes a problem because what happened if the I cannot fit this stuff in memory? That's one part of the limitation. Hash tables are useless if you can't fit them in memory, right? Because the whole point is, because the whole thing is an array, you have to fit the array into memory so you can use the byte addressability of the RAM. Again, unless someone invents a byte addressable disk, all of these problems will go away, hopefully. I think there are a lot of attempts. Ultra RAM was the latest that I'm aware of, which is basically a persisted disk value that is just as fast as the RAM, but is also persisted. I'm going to reference the video that I talk about Ultra RAM. But yeah, a lot of the storage people, they talk about this. They eat this for dinner, effectively. But yeah, this is the idea of hash tables, hash joins. Very, very popular concept. Now I want to talk about the limitations of hash tables. And this is where you really kind of link to the previous topic with hash joins. Basically, watch out. Again, hash tables have to fit in memory to be utilized. And that's the biggest problem, I guess. It's like, what happened if you, because that's the first thing people will say is, hey, I'm going to build my entire key value store as a hash table. Hey, let's put the entire customer database as a hash table. You can't. How? How much memory do you need to put the entire thing in memory? Because that's what you need to do, right? Let alone just building that goddamn thing. You need to build it first. And to build it is costly, because to build it, you have to scan the entire thing. That's a big O of N. You can scan the entire thing, pull it in memory to build it, and that's a cost. Maybe you can consider this a fixed cost, right? And then once you build that, then you have to, all of that, get it in memory. Otherwise, if it's not in memory, you have no idea which parts will be fetched next. I think you can play games here where you can play the idea of having, I don't know if you have low-level access to the RAM, where you say, hey, if someone access this location and it's not in RAM, go fetch it from disk. You can build data structures like that, I believe. But I don't believe it's going to be easy, right, to do that. Maybe they do exist and I'm not aware of them. Please let me know if you have worked with such like disk hybrid model. But that's the idea. That the limitation is the memory cost. You can't just have a billion size hash table. Plus that's one thing, the key size, and the other thing is the actual values, which is might not be as problematic because they can live somewhere else. The actual pointers. It's just the indices is what is critical, and then the pointers can live somewhere else, in the heap of the memory. They don't have to be consecutive. Like a string is not really literally a string that lives in the element itself of the array. It's a pointer to some other location that we don't care about. As long as we have that pointer where we can jump to that memory location, then it's fine. Yeah, it's an extra cost of the CPU, but Intel and AMD and all those peoples are taking care of these optimizations. But yeah, this is all two limitations. The cost of building the hash table is a cost, right? That's why you always pick the smallest in case of a join, right? The other one is the memory. Like you have to make sure it fits in the memory. And there are workarounds for this. I believe one alternative to hash joins is to avoid probing all over again, because you have to scan this other relation to always just go back and jump, right? And that can be costly if you do it over and over and over again. So you can effectively partition stuff. It says, okay, let me just work with a smaller subset instead of the entire table. Let me just create partitions. Any value that I'm scanning, I'm going to create a partition that is closer to each other, and then I'm going to store it to disk, and then read the partition from disk, and then hash table that. This way, you don't have to scan the entire, build an entire hash table of the entire relation. You just partition it and chunk it. Work with it smaller size. So that's another limitation. There are workarounds, obviously. The final thing is really what the biggest problem with hash tables is what happens if I want to keep adding new keys. I want to delete a key. I want to add a new one and delete one. Deleting and adding to a hash table really screws up everything. Why? Because remember, we're doing a hash and then we're doing a modulo on the size of the hash table. So now if you have a value and you hash it and a value of like from 0 to 10, like the value you hash it, you do a modulo on 10, then you get a value from 0 and 9, right? So I say you get 8. But what happens if you add another element, right? Now your hash table is 11. Now the modulo operation, if you do it modulo 11, you're going to get a different value. And now you're not pointing to the same index anymore. So you have to do a remapping after you add or delete. And that is costly, right? So you have to scan the entire thing and then just reshift things. It might not be as expensive. Sometimes it's easy. Sometimes it's slow, But that cost of remapping, you have to keep it in mind. Sometimes that's why people just say, okay, I'm gonna work with I'm not gonna resize my hash table. It's always gonna be, I don't know, it's always gonna be 10, And as a result, you don't anticipate that it's gonna be increasing, right? But again, if you fix it too large, then you're consuming a lot of memory, and you might have gaps. If it's too small, then you might add values to the hash table, and that will cause remapping. And that's a problem with Cassandra and any sharding database, a distributed database, right? The problem is to do sharding, you kind of use a hash table, right? Because if I'm doing a query and this is my node, right? You don't really specify a node per se, but you're based on the key. So like if I'm inserting value 8, you hash that, and then the value will map to a node or a shard or a partition. Even partitioning, you can do hash partitioning. Right? I'm talking about hash partitioning here, not range partitioning. Range is easy. It's like from 0 to 10,000, go to this server. From 10,001 to 20,000, go to this server. From 20,000, you get this idea. But if you are using hash-based sharding, then every value is hashed, and then you calculate an index, and that index point to an array, and the value of that index in the array gives you the server name. Then you hit that server. But what happens if you add a new server? Then the whole thing changes, right? Then what do you do? If it changes, then all of a sudden, if you try to read a key, and instead of going to that particular server, the remapping has changed. Now you're going to another server and you're not going to find the key. That's why Cassandra sometimes struggle with this. When you do a remapping, it's really hard. They solved all these problems, but I'm just discussing the original problem here, right? I say struggle, I say initially, right? So like if you add something, a node to the ring, then the neighboring rings has to share values, because now you're remapping keys. So if I'm adding value to a node, I need to join this value to this ring, this cluster, and now I have to borrow values from my neighbors based on this remapping. Because now I no longer hold this key after this remapping. This guy holds this key, so you have to reshard. And this is where another concept was invented in 1997, I believe, called consistent hashing, where they try to minimize the effect of this remapping, because remapping is expensive, right? So consistent hashing, maybe another topic, solves this to minimize the effect after adding or deleting a node. Because remember, in distributed architecture, you're going to add and remove nodes all the time. So consistent hashing, the idea of having to consistently always hash to the same server no matter what, is very, very critical. And maybe that's another topic for another day. I hope you enjoyed this episode. I'm going to see you on the next one. You guys stay awesome. Goodbye.
In a previous episode of the Backend Engineering Show, I talked about hash tables and how powerful and very commonly used they are. Given a key, we can find its corresponding value in no time, in zero seek time. We're not searching, we're not scanning, we're not doing anything. It's a single access in memory retrieving that value. The power behind hash tables is the use of the arrays, which is a very common data structure, obviously. A very, very common data structure, right? Knowing the array position, the index, you can get the value of the array immediately, because you know how does memory work? If you know the address of the RAM where your cell exists, where your values exist, you can get the value immediately, right? The CPU can fetch the value immediately for you, right? So once you find the index, you find the address, you can get the value. So what the hash table guys did, it says, okay, we're gonna take your name, your string, your color, your car, anything that represents this key. We're gonna hash it using a one-way function, and then convert that into an index using a modulo function based on the array size. So we eventually, from the name, we convert and getting an index, and that will give us the address and the memory, and we can get the value. So that's the trick the hash table guys use. You know? So the only cost you add is like what? The hashing function, which is not really that bad, but that's the power of the hash table. But the problem is, the moment the size of the array changes, the hash table size changes, this all falls apart. Yeah? Because if blue, the key blue, used to fit in index number 11, if you increased or decreased the array size, and you know where I'm going with this, then the blue will fit into index 99 now. And as a result, right, you either won't find the value, or you're gonna start writing the values duplicate, and everything will basically be bad. So you now have to really move things around when you resize, and it's really a big problem. So why I'm mentioning that? The problem that we are seeing today with distributed system is as follows. If my database are increasing in size and it no longer can fit in a single instance, I bumped up the vertical scaling to its maximum. It's now 48 core CPU, 3 gigahertz, whatever, you know, it's 512 gigabyte or even 1 terabyte RAM, but it's still, I have billions of rows. I added all the indexes. I tried to partition it horizontally in the same instance by range. So, but it's still, even the partitions are so large. So that machine cannot handle the queries I'm throwing at my beautiful database. So what do? We distribute it. We shard the database. I really don't like to go there unless I kind of exhaust all my options, and believe me, people don't even look at the options anymore. People are very quick to follow modern things, you know, without actually going to the basics and trying to tune your database and getting a better performance. But regardless, let's assume your YouTube scale, let's assume your Google scale, and you run out of ideas. That single instance can't handle anymore. You need to distribute that billions of rows table or key dictionary or collection into multiple servers, right? So instead of having billions, let's have, few millions on this server, and few millions on this server, few millions on this server, few millions on this server. Immediately a problem occur. The problem is like, how do I know, right? If I have a key, I want to look it up. We introduced an intermediary problem, right? That didn't exist before. Well, first, if I have a key, I go to my database server and I ask it, and it immediately give it to me. I only go to one hop. Now, if you're distributed and you only have the key, you have to answer the first question. Which server should I connect to retrieve the key? Which server hosts my key? And that is the problem here. That is the original and only problem that we have in distributed system. Which server should I connect to fetch that key? Right? So the trick was always, let's figure out the server from the key. And that is the concept of hashing. Hashing tables appear here. So in this episode of the Backend Engineering Show, I'd like to talk about that a little bit, distributed hashing, and then what problems did we have and how consistent hashing solves this problem. And obviously, nothing is perfect in this world. So I'd also like to talk about the problems consistent hashing actually have today. Welcome to the Backend Engineering Show with your host Hussein Nasser. And the concept of distributed system is a must when you get to a certain scale. Yeah, I always try as much as possible to, push people against being distributed if they can do things to have their single instance, be more performant when it comes to query. Because you see, a lot of people, a lot of engineers hurry up to scale, right, and spend more money to start to work with the distributed without actually, while their query is actually using 500% of their CPU and then doing like a million logical reads, where they can tweak it a little bit, tweak it and tune the database a little bit, understand their queries so they can half or even lower that cost, as a result. But we don't think this way anymore. We always take the shortcut, unfortunately. But regardless, so usually advanced and adept DBAs try to optimize a single query. As a result, if you can get a query to consume less CPU, even if it's a small query, scaling that query, right, will eventually give you better scaling on your instance. But that's not our topic. That's another day. But let's say you reached a state where you exhausted all your options, when it comes to a single instance, right? Then you moved. It says, hey, I have to move to a distributed system. It's just too large. You gotta move. So people, what they did, says, okay, I have a key. And now I don't know I have 10 servers, right? I don't know where this key lives in this 10 server environment. So I said, all right. So what we're going to do, let's say I have 4 servers, a cluster with 4 servers, and I want to distribute my values across these 4 servers. So server S0, S1, S2, and S3, right? What we're going to do is like giving the key, I need to know the server name, the server IP. And that's something that we are introducing as a problem, right? We introduced a friction that didn't exist before. Previously, it's just one server. We know the server, right? But now we have to figure out from the key, we have to figure out the IP address of the server to connect to in order where our key actually exists. That answer can be answered using a very simple hashing function. So we're going to hash the value. Let's say I have value number 4. Going to hash it, get some value, and then that value we're going to do modulo number 4, and that gives you server 0. So store server 0 right here, right? In this case, right? So 4 modulo 4 is 0. And then, okay, how about key number 5, right? Or even whatever that key used to be. Maybe let's say it's a blue or red, right? Red, you're going to hash it, get a value number 5, which is a number, and then 5 modulo 4 will give you S1, and S1 will go right here, right? So 5, right, lives in S1. And same thing, 6 will live in S2, and 7 will live in S3. You're just going to do modulo 4, because 4 is your server pool size, right? And then let's say going back, let's say 8, then 8 modulo 4, so back to 0. And then you get the point, which works perfectly. From the key, I was able to figure out the server. So cost is 0, is nothing. We solved distributed system right there. Here's one problem though. As long as you have 4 servers, your life is beautiful. You don't have to worry about anything. But now, even those 4 servers reach their limit. Again, whatever reaches the limit, that means you're at the globe scale. You have so many users, right? So to me, that I need more than 4 machines, database instance, that means I am at the global scale and I have users left and right, millions of hits, So that's the scale we're talking about, right? So I say, okay, all right, let's just add another server. Server 4, S4. So we have S0, S1, S2, S3, and S4. Sounds good. Comes back to the problem of hashing tables. The moment you change the size, whatever value were original, so the values, their original key values, are now all shuffled, right? Previously, value number 4 you do 4 modulo 4, the key 4 used to live on server S0 because 4 modulo 4 is 0. But now 4 modulo 5, which is now the new servers, we have 5 servers, is actually gives you value 4. So it's now is an S4. So now what you need to do is like move the key with value 4 from the server 0 to server 4. And now you have to move everything else. And this is basically the same thing. 5 modulo 5, right? The server 5, the key 4 will move to server 4, the key 8 will move to server 3, the key 5 will move to server 0, the key 6 will move to server 1, and the key 7 will move to S1, right? So everything will be shuffled, and the operation of adding a new server will cost us a huge amount of effort to kind of shuffle things around. So think about networking, think about database usage just to add another server. So you're not only bothering one server, you're bothering the entire cluster with your operation because you have to shuffle things around, right? Because your key no longer maps. So what people think, what the smart people say, okay, let's invent something that might solve this problem, which is called consistent hashing. So how does it really work? So they went back to the idea of having, the core idea. We use the index as the server names here, right? Let's flip this. Let's change this a little bit. Let's not be very discreet, like, server 0, 1, 2, 3, 4. Let's build a ring. Let's actually build a ring of these servers. All right. So instead, they think of this idea as an actual ring, as an actual circle. So values go back, right? And remember, a lot of people thought a lot about this to solve this problem. And the key here is, instead of the output of the key hash going to a server, we're going to approximate it, by using this concept of the ring. So let's take an example so clarify it. The first thing we're going to do is the servers themselves, we need to fit them on the ring, which this is something we didn't do before. So the ring is, think of this ring as a circle. So the degrees, based on the degrees, this is a 360 degrees, right? So let's say server 1, you're going to do a modulo 360. Let's say we're going to get a 0. Right? So we're going to put server 1 and we're going to call it S0 based on the degree here, right? And then let's say server 2, IP address 10.0.0.3, modulo 360, we got 90, right? And again, I'm picking values that are so rounded up. This is just for example. You're hardly going to get S90, right? Exactly, right? You're going to probably get S27, right? But yeah, X90. Same thing, server 3 or server 4, you're going to get S180 after you do that. And then server 3, you're going to get S270. We have S0, S90, S180, and S270. That completes an actual ring. And for people listening in the podcast, think of this as an actual ring with the values for servers in each corner effectively. So why are we doing this? The beauty here is, we have values, and this is the key here. Let's have a key value of 1,000. Same thing you're going to do, right? the 1000, the key value 1000, right? However this key exists, maybe it was blue and then you did a hash and then you got the number 1000. You take that 1000, right? And you do a modulo 360. Will you get an actual server immediately, the server index? No, you're not going to get that. So now let's actually put it in an actual examples right here, right? So now I'm about to insert a value. I'm going to insert a new key. Value 1500. That's my key right there. So what you're going to do is you're going to do modulo 360, which is this circle. Again, don't be very specific on the value 360. You can double this and double this and double this to get more values. But again, this is just an example. So 360 here. So if I take 1500, right, and modulo 360, I'm going to get a value of 60. If you think about it, S60 doesn't exist. There is no server marked 60. But here's a trick. We do have a server marked as 0, and we have a S90. So S60 really fits between the 0 and the 90. And what you do is you pick the next one. So 60 fits between 0 and 90 immediately. So that key will go to the next value, which is S90. And that's how you do it, basically. Now, visually, this is easy to understand, right? Computationally, this is not as simple. Because what does that mean between 0 and 90? I have 4 servers, and that's easy. To find where your value how 60 fits between 0 and 90 is actually computational. And that's another binary search to actually find that value. That's a little bit outside the scope of this video. But now once we have that value, we have the 60. Now, okay, 60 is like, what's right after 60 is 90. Now, okay, so value 1500 fits on server S90. That's how we solve it. So by doing this scan, what is the next one? We really remove that discrete value lookup, you know? We instead changed it with a scan. And the beauty of this scan is going to save us a lot of things in the future. Let's continue these examples. All right, 1500. Let's take another example. Let's say 2000. 2000 modulo 360 is 200. 200 fits between server S180 and server S270. Again, 180 and 270, think of as degrees, right? So right there. In this case, okay, what's exactly right after 200? It's 270. So 2000 lives in 270. So think of it like you're looking at clockwise. So whatever is the next value, you're going to get that. And then you put another value, say 3000 modulo 360. That's 120. 120 fits between server 90 and server 180. So like move directly to the 180 and then you store the value 3000 there. How about 1000? 1000 modulo 360 is actually gives you 280. Wait a minute. 280 is there are no server after the last server with the largest value is actually S270. There is no larger after that, right? There is no larger than server 270. This value is 280. So what do you do? If there's no larger values, you go back to the circle, right? And this is very nicely, when you actually draw the circle, you see that S280 is between S270 and S0. So you immediately go and put the value 1000 in server 0. And that's how you build the ring. Let's take another example for completeness here. 4000 modulo 360 gives you 40. 40 is between 0 and 90, right? Oh, that's very nice. So now we have 2 keys lives in server S90 in this case. Yeah, that's very interesting. Let's spice things up. Now, what if I added a new server here? Look at the beauty of this here. Now, if I add a new server here, let's say its IP address is 10.00.13, right? I do it modulo 360 and I got 50. So now my server is actually S50, fits right between S0 and S90. Keep that in mind. Now, things change because we still need to move data around, but not as much. Let's figure that out. How much data I need to move around? Well, the algorithm goes like this, right? Remember, if you have values, if you add values as 50 in this case, anything between the 0 and the 50 really needs to be fed in server 50, right? Because that's the algorithm. That's the range here that we're looking at right here. And so if you, the algorithms look like this, like, okay, so what is the server right after me? Well, the server right after me is right here, is 90, right? So let's query that server, find out all the hash values, where the actual hash value is less than 40, right? Because S90 would have stored everything between 0 and 90, right? So find out everything that is less than 50, because I should store these now, right? So we found one entry, which is 40. Oh, 40 doesn't belong 90 anymore. So go ahead and talk to server 90, establish a communication, could be TCP, could be anything, and then start moving data around, right? Hey, it's 90. And do you have anything with a hash value that is less than 40, less than 50, which is me? Oh yeah, I have this value. Move it to me. And as a result, we just establish the data here. So now think of it as I add another server, the only change is my neighbor, really. I'm only gonna not bother my neighbor, and it's only the neighbor right after me, right? That's what I'm gonna do in this case, right? And so instead of actually bothering all the servers in my cluster, I'm only bothering one server. So that's much, much, much better than actual hashing. But still, there is a cost to it, right? There is complexity. You need to build all that out. What if the operation failed? How do you roll back? What if, do you add a server anyway? What if one of the keys didn't transmit? So we're adding so much complexity. So distributed systems are not easy, you guys, right? Even if you think about it, let's take another example where we're removing a server. If we go back to our original case where we have S0, S90, S180, and S27, and let's say I'm going to remove S90 altogether. So now what happens here, if you remove S90, then anything that S90 had must go to S180, if you think about it, right? Because any value. So now what happens is the operation should go, okay, remove server S90. That is the operation that we need to do. Right? I'm going to remove that, physically remove it. Not talking about a crash. That's a completely different story, right? Crash, you don't even have time to move anything, right? So that's why you have to have redundancy. That's another complication right there. But if I have a physical operation that say, okay, I want to remove this for maintenance, remove S90, well, S90 holds all values between 0 and 90. So all of those should go directly to the server right after me, clockwise, which is 180. So remove all those puppies and stick them to where? To server 180. That's a very expensive operation as well. So if you think about it, consistent hashing is powerful. The algorithm of consistent hashing are very powerful. But the limitation here becomes you still need to move data around. And the more data you have, in these instances, then the transmit of these will take more time. So adding or removing server is actually not a trivial operation. And then you really need to think about another thing that is called replication. You need to duplicate this data as much as possible because a server might crash, so you need to have a backup. So just using this algorithm blindly is not enough. You have to cater for crashes, and as a result you have to have a backup. Oh, if this server is not available, let's have a mapping server that actually directly copies that data immediately, right? So that's what you do. You have to do that. Well, what if two servers map to the same hash? You can't have that. If you have a lot of more than 360 servers, you're bound to have the value that fits on the same server. And I'm not sure what you can do here. What you can do is, like, I suppose in this case you can treat it as a replication. So you have like a backup scenario where we have this server. You can either put it in both. Right? That was an episode of the consistent hashing. Hope you enjoyed this video. I'm gonna see you in the next one. You guys stay awesome. Goodbye.